this session we're going to examine the behavior of a circular solid shaft subject to a torque at the tip. And this shaft is made of two materials. Material 1 on the outside and material 2 at the core. To analyze this problem, we have to write the equilibrium equation and the compatibility equation. The key here in terms of compatibility is to realize that the rotation that the material, the bar is going to experience at the tip due to that torque, we're going to call that angle of rotation phi. And that phi is the same for the material at the core and the material on the surface, material 1 and material 2. So this whole thing rotates the same amount. Right? And that's where we get our compatibility equation, where we say T1, which is the torque in material 1, the proportion of T that goes to material 1, TL divided by GIP, that's the rotation angle, and T2L G2IP2 is the rotation angle in the material at the core. So they both rotate the same amount, and this is where we get our compatibility equation. And from here, we can determine the relationship between the two torques. The torque being supplied by the material at the surface, and the torque being supplied at the material from the material at the core, 1 and 2. Right? So this tells you the ratio between them is going to be equal to the ratio of their stiffnesses. If we take this and substitute it in this equation, we get this. We substituted T2 in here, and now we can solve for T1. Before we do that, we just have to carry out this sum. And the way we're going to do that is basically we're going to multiply, this is a 1 in disguise here, right? And we're going to add it to this. Then from here we add the numerators and solve for T1. So this tells you that the proportion of the total torque that is going to material 2, it's going to be the ratio of the stiffness, the torsional stiffness of material 1 divided by the sum of the stiffnesses. This is a similar result to the one we obtained when we had a column made out of two materials subjected to compression. The total amount of compression going to one material is the stiffness of that material divided by the sum of the two. So the same thing happens here. The torsional stiffness of material 1 divided by the sum of the torsional stiffnesses gives you a ratio between 0 and 1, And that ratio, that proportion, is the proportion of the total torque that's going to that material. If you take this and substitute in here, you'll get that the proportion of the torque that goes to material 2 is, not surprisingly, equal to the torsional stiffness of material 2 divided by the sum of the torsional stiffnesses. So that's T1 and T2. The amount of torque going to material 2, the amount of torque going to material 1. Now, once we've got the torques going to each material, we can find the stress. In each one of them, right? So we know that the maximum stress in material 1 is going to be T1 times R divided by IP1. Now, we have to keep in mind here, and same thing happens with material 2, right? T2 R divided by IP2. But you have to remember that you have one here at the core, another material here on the outside, and when you look at the stress, the shear stress, right, you're going to get something that varies linearly here like that. This is for material 2, which is at the core, and then material 1, which will have a discontinuity. It'll not follow this same straight line like that, because it has a different G and a different IP. And so in this case, it might be something like this. So you'll have a discontinuity between material 1 and material 2. And you can solve that from the equation. So if you write tau 1 equals to T1, which is, so you have G1 IP1 divided by this times R divided by IP1. This cancels, right? Then you get, this is times T, right? Then you get tau 1 equals to G1 times R. Let's call this R1 times T divided by G1 IP1 plus G2 IP2. If you do the same calculation for tau 2 at the same point, so the stress in material 2 at the same point right here, right? You will get G2 times R, right? Let's call this distance here R, from here to here, times T divided by G1 IP1 plus G2 IP2. So you can see these two numbers are not the same. So there is a discontinuity there between the stresses that you see in material 1 and the stresses that you see in material 2, and the ratio is going to be equal to the ratio of the shear moduli, right? If you take this and divide it by this, the denominator is the same, the R and the T, I'm sorry, this should be T right here, the R and T cancel out, and basically you get G1 divided by G2. So this will be the shear stress distribution across the cross-section with a circular shaft made out of two different materials with two different shear modulus and two different polar moment of inertia.